Neural networks appear in our case in computer vision, but in general, it's the part of machine learning problem. And maybe, well, let's think that you are familiar with the problem of machine learning. If not, I will say just one word, that the problem of machine learning is can be formulated as is presented on this slide. If we have some kind of input, and for instance, we know what should be the answers. The idea is to build the function that can convert these inputs to this particular outputs, but this function, well, this function is unknown, and we want to build that function, the function A, that behaves the same as the function y with a star for not only for this particular input signals, but for any signal. So once again, if we have some kind of sample for input, some sample for answers, we want to build the function, let's call it A, that provides the connection between not only these particular pairs, but for any x in the world, and to hope that it will be exactly that function that is considered. This task may be solved in different ways, and if you want to know more than Google machine learning, today we'll speak about how to solve this problem in with neural networks. Why do we need this in our course of autopilot? The idea is, well, comes from the previous lecture when I was talking about video recognition. There was not recognition, there was segmentation. And we want to, well, clearly the most, from the highest point of view, the idea is to, according to a video frame, to find a particular object on this frame. And we can reformulate this problem and say that, for example, we want to, if there are some pixels on the video frame that are grouped in one particular manner, we want to say that these pixels should be considered as some object. So in this case, sample would be input, it would be just the pixels, and output would be the objects that are placed in the image. This is one of the problems that might be solved. Maybe with the same input, we want to solve another problem. For example, we want to say what else can I think out? Maybe we want to say that for this particular pixels, we want to find the largest object, for example. Yes, in this case, we want to group, not only to group the pixels, but also to find the size of objects. And so the idea is that it doesn't matter what exactly is the output. For any problem, we are able to formulate such problem for any problem, such equation. For any problem, we can say that we're looking for some particular function. And today we will consider only the common approach of neural networks. We will only say some general words about how do they work. And I will say, we'll provide several networks that are widespread. I won't show you any example of, how to say it, applying of networks for video recognition, segmentation, or so on, because it's how to say, you can Google it by yourself. It will be like magic box for you that does something for you. The idea of this lecture is to say what's happening inside, but without complicated structures of networks. Because it's complicated to find out what's going on even for one neuron in the neural network. You'll see what I'm talking about. Okay. So once again, input, output, real unknown function, the function that we build. The one basis term for neural networks is the neuron, and its idea is pretty the same as the neuron in our brain. For some inputs to generate output. The input for the neuron are just the signals x1, x2, x3, xn, and the constant that is called bias are just inputs that are provided with some weights. And the easiest way that we do, we just sum these input signals with this weight. Then we apply here to set the threshold unit. Then we apply some function to the sum and generate the output. In the easiest way, there can be no extra function. We can just say some weighted sum. We can create some again sum. We can create some any sum. Why? Sorry. So let's find out how can we and the idea of training of such network is just find which weights here can solve our what was it, this particular problem. So the idea is to create this function according to the weight on the net. Our function would be the core of this function would be in this weight. Let me say more precisely. If we have some input signals, if we have some weights, we can generate the weighted sum or the dot product, which is the same, and have some activation function. And the idea is to change these weights in that way, to say to provide the correct output to this particular signals. What's so complicated about that? The problem is that if we always know the input signal, then there is no problem. If, for example, there are only two inputs and they have only two different types of signals, for example, x1 and x2 might be only zeros and ones. And we have to generate some kind of output for any particular combination of these signals. In this case, there is no training. There is only, in this case, there will be only for one iteration, we will find the particular weights for these signals, and the process of learning will consist of one step. But if there are more possible signals with more possible degrees of freedom, then we cannot predict the particular sequence on X, and in this case we have to say something about approximation or so on. Let me show from the easy example to the more complicated. For example, if we have the weight like this, for example, what will we have with this exactly this weights? You see that if we have x1 with weight 1, x2 with the weight 1, and 1 with the weight minus 1.5, that would be exactly this formula for sum of these parameters. And if x1 and x2 may have only 0 or 1, then we will have well, that's not correct. I'll put it written here. Let's find out what we will have. If we have 0 is 0, then we will have minus 1.5. If we have 0, 1, we will have minus 0.5. If we have 1, 0, we will have minus 0.5. And we have 1, 1, we will have 0.5. So here we get only the signs of these values. This example of neuron, or it is called perceptron, is the example of if we, for example, apply the sine function to this output, then this function would provide us the positive value if the both incoming signals are 1 and 1, and negative signal if they both are not 1. Do you know any existing function that behaves in the same way, that outputs something if two variables are the same and they are 1, and another output if they are the same and if they are not the same and they are not 1? Of course you do. This is AND function, not XOR. XOR would appear if there would be 0, 0, 1. But AND function is exactly this. Yes, if we have anything except ones, then we will have minus 1 or 0. Well, we have not the same output as here. Using gate and what? Yeah, yeah, you're right. Yes. The only thing that we have to change here is to say that we have to apply to these values some updating function like this. So it would mean that when we get, I erased it, when we get anything positive, if s is greater than 0, then return 1, else return 0. Instead of sine function, we will change it to the to this function, and that would be exactly AND function. It is useful to visualize it, to see how is it looking in the two-dimensional plane. Basically, this equation is exactly this line, and its derivatives by x and x1 and x2, its gradient is 1, 1. So it is phased exactly in that way. So it shows us the border between outputs, and shows the dimension which exactly output is placed in one possible cluster of outputs and which to another. Looking at this approach, we can say that if we change the angle of the line, if we will shift it, we can change the output of the whole network that consists of one perceptron. So if we just shift it a little bit, we'll have the example of OR. Yes, for AND, for one cluster, this is 1, 1 for x1, 1, x2, 1, and anything and everything else, 0, 1, 1, 0, and 0, 0, corresponds to another cluster. For OR, there is another way. 0, 1, 1, 0, and 1, 1 should be united to the one cluster, and 0, 0 to another cluster. We want to find out the equation for such line. It is clear that there might be several lines that do exactly what we want, that divides the plane for these two clusters. If we have only these possible inputs for x. Well, let's find just any equation for this line. First of all, well, here we have already the answer. If we have such function, well, on the next slides I will show you how to find out this function. If we have this function, then just creating this kind of table, we will see that output exactly that we wanted. Yes, 0, 0 minus 0.5 is negative. If at least one of them would be 1, then it will be positive. Yep, and then we have exactly the output for OR that we expected. But in general, how to build the process if we have a lot of different points, not only two with two particular coordinates. How to build the line that divides two different, there should be the GIF animation, but since it's PDF, there is no GIF, unfortunately. Last square root. Well, yes, but if we're talking about one perceptron, there is not least there is nothing to sum under this root. So for one perceptron, this is very straightforward. It is just several iterations. I will show you right now. But if we're talking about several perceptrons, yes, it will be a bit further. What's the algorithm for creating the line that divides on two different segments? Let's find out. There also should be the GIF, very visual. Give me a moment, please. Give me a moment. It is not in this on this computer. Oh. Okay, then no GIF, no animation then. Sorry. Okay, let's look at on the algorithm. What's the idea of the plan? Not of the plan, of the learning. First of all, we put all the possible weights to 0. Yes, I remind you that all that is named by W are the weights for incoming X signals, and B is the constant. Then we should specify several iterations. Well, the amount of iterations depends on the amount of input possible data. Then we apply for every particular coordinates of X. X is just the coordinate of the points. We apply this particular weight and calculate for and look at the in our case the sign of the sum. If it's positive, then if the value of the sign is the same as we expected, then we have do nothing. We should do nothing. If the sign, well, it is written over here, if the sign of the multiplication of the real output and the calculated value differs, then we have to update W and V. And we have to update in a very straightforward way. We have to add the answer. Answer might be whether 1 or -1. That is multiplied for the incoming input. And that's it. We just to have iteratively update weights by adding some preset constant. Let's see if this works. I won't like prove it to you that this algorithm works, but I will demonstrate it. How does it work? For example, we want to create the line of or. For example, we don't know that it is exactly this line. For example, we build any line like this with weight 2 minus 0.5 and 0.3, for example. Okay, and let's well, these are not written yet. Let's think that this column is not written yet. Let's look at the real answers and what we get for such line. Let's put here in this line 0, 0. 0, 0 gives us, why it gives -1? It gives us 1. If we put here 0, 0, okay, we put here, not in this line, but in this line. It doesn't matter where to put it, but it will be more consistent for this output. If we put here 0, 0, we will have that 0 is equal, not here. Well, not. I'm wrong. We should put it exactly here. But why? What is wrong? Okay, let's find out. Let's rebuild this column. If we put here 0, 0, we will have 0.3 that is greater than 0. If we put 0, 1, there would be 0, 1. There would be minus 0.5. That is lower than 0. If we put here 1, 1, there would be 2 minus 0.5 plus 0.3 would be 1.8. That is greater than 0. And if we put here 1, 0, it would be 2.3, that's also greater than 0. And in this case, we have what? We have 1 here, minus 1 here, and 1 here. Okay, this is not the same that we have over here. Well, we have at least 2 options where we differ from the real output. We can choose any of them, any of the not corresponding values. Well, let's check this one, just because it differs from 0. And the only thing that we have to do, we have to add this to this value and this to this value. Yes, we found that there is one of the lines where we have the difference in our output and the expected output. And we just added these values to these weights. Bam, added. The first weight is the same, here plus 1, here plus 1. Okay, let's look at this at this output. What we have with this equation. 0, 0 would get us plus 1. No, I mean positive something. 0, 1 would give us also positive. 1, 0 also positive, and 1, 1 also positive. So we have positive everywhere. Positive, how to say it, positive value of sum. But we expected over here that here we will have something negative. All right, then we have exactly this. How to say it? Here it is placed the changes that we have to do with this particular weight. So we have to put it the same. Here would be the same, and here we should subtract 1. But Exactly that we expected. Okay, let's look at this more precisely. Once again, put here all these values. We will find that here we have, once again, everything will be positive for every value of x1 and x2. But we expected here negative. So we do it once again. We subtract here one once again. But there should be 7 over here. And looking at and here also 7, and here also 7, and here, well, this is the wrong one. So look at this equation. We'll find exactly that everything on the output corresponds to the real answer that we expected. And this is this line. So that was the process of learning iterative. Once again, I'll show the slides quickly. We started with any line, found one of the problems. Well, here I chose exactly this value, but I could start with this one. It doesn't matter where do I want to start. I've chosen this amount of values that I added to this particular weight. Then I did it once again. I found the wrong input that did break our result. I added once again. Well, I subtracted 1 over here, and I did it once again. I subtracted 1 from this once again, and this brought us the line that divides input exactly in that line that we wanted it to be. This is one of the possible lines. Here we see that this coefficient didn't change at all. If we wanted to be more, how to say it, more sensitive, we could add these values with some multiplexer, with some parameter. They would do exactly the same way, but with a little more, how to say it, more sensitive it would be. But the idea, the common idea is that after some iteration, after several iterations, we will have the line that divides the plane exactly in that cluster that we expect. The only problem that here we have is that we have all the possible combinations, and we know all the possible outputs. And this works for the situation when we all here things we know. For example, if we somehow extend the OR rule for float values, then we will have to make more iterations, add more training points, and hope that we will have enough training points for every situation. For example, if we have, if we say that if we would create the OR rule for float numbers with exactly this line that divides them, then we'll have to make sure that we provided this point, this point, this point, and this. Because, for example, if we forget, if we specify only this, and this point, then there would be several possible lines that brings us such division. And this is the general problem of learning. that we have to provide the most border, how to say it, situations for the learning. In other case, we might face to the problems of wrong learning. But it is not the only problem that we might face. For example, if we have XOR, how to build the line that divides the plane in these two possible clusters? Well, no way. The division might be like this. And this comes with several neurons, where we have several lines. Every of the line might be shifted in any way it likes. And once, for example, it is one of the possible examples how it can be divided on the clusters with several neurons. Okay, so I hope that for one neuron it's pretty clear how does it work and what to do if your network contains only one neuron. But in general, it would be not such simple neuron, and there might be several neurons. Well, what I'm talking about, not this type of neuron. Here we had our activation function was just the sign of the sum. Yes, if it's the two-dimensional plane, that's possible. Yes. Yeah, I'm talking about exactly about two-dimensional plane. About more complicated inputs a little bit further. In these examples, our activation function was only the sign of such sum. Yes, we looked only on the sign, but and the sign and the graphic of the graph of the sign is exactly this. But in general, we might have more complicated activation function. There will be some kind of something like this or like this, doesn't matter. For different tasks, there might appear different activation functions. The benefits of such functions is that we can take the derivatives. Sometimes it's important. I will explain where it might be important on the next slides. In general, when we're talking the neural networks, we unite several neurons and and specify the connections between them. In general, there are three clusters of layers, where every layer consists of only neurons. One layer is the input layer, and here might be not exactly the neurons. Here might be the just transformers from any input dimension to the dimension that we're looking for. For example, if we're looking on the picture on the array of pixels, for example, input layer might convert this image only to one-dimensional array. For example, by one-dimensional, I mean that if we had some kind of two-dimensional array, it just put it in one-dimensional line. Maybe it's just an example. And here we have that amount of inputs. How many values do we have in array? And in this case, we will have, for example, for image, I don't know, 10 on 10, 10 here and 10 here. We will have 100 values, and we will have 100 inputs in the input layer. For example, just example, we have the output layer. Sometimes it's only one value, for example, 0 and 1. For example, if we want to find if there is something on the image, if there is a dog on the image, it will output yes we have or not or no we not. And somewhere in the middle we have any amount of hidden layers where every layer consists of several neurons. Every neuron, well, it doesn't matter if I say neuron or perceptron. They are pretty close terms. They differ only on the activation function. Every neuron here does exactly that way that we talked before. It has some signals and adds them with some weights. Here, let me say, here L is the number of the layer. Well, if we have some signals on the layer number L, then output would be with number L plus 1. And what is K? I don't remember. Well, here the lower index, first lower index is just the number of the input signal. And what is K? I don't remember. Maybe we will see it further. Well, the general idea is very simple. We have some inputs. We know that for any input, we should construct the output. We can provide some outputs for some particular inputs. We have to calculate for every such connection that weight that would provide for every known input the known output, and to hope that for any unknown input it will provide the correct output. The greater amount of known pairs of input-output, the greater possibility that for any input the output would be correct. But we never know. If, for example, we train our system only on dogs, it would never find out if there is the cat on the pixel or on the image. And for example, if we train our net only on dogs, I don't know, with 4 legs, it will never find out the dog with 5 legs, for example. And this is the risk that any developer should face if he decides to apply the neural network for his purposes. So in general, the data sets for training sometimes, I don't know, contains hundreds of gigabytes of information, just to make sure that every possible situation is considered at least once by a neural network. But still, the question of how do we calculate several weights? Yes, for example, we have here 1, 0, 0, and output should be 1, for example. Which weights should we put on in every step to provide it for this output? And how might they change if I change input and output, and it still should be correct? Well, there should be some algorithm that should be straightforward. Let's find out. Let's reconnect here because we are out of time in Zoom, and I'll carry on. And here, when we're talking about the calculation of common weights, not common is the wrong word here, of all weights in the network, we're talking about the minimization of some functionals. Let's look at the one perceptron more precisely. For example, if we know the true output of this particular perceptron, we can calculate the loss function. If this is the correct answer and this is the answer that we gave, then we can calculate the loss function. And if we can collect this loss function for every neurons in the layer or in the net, in the whole net, we can calculate the quality functional that we should minimize. and minimize it by A. Minimize it by A means the same thing that we want to minimize it by W. How to minimize the functional? Gradient descent, the only known approach that is widespread and the best known for these purposes. Yes, I hope that everybody is familiar with gradient descent, but just a couple of words. If we want to find the minimum of some function, we choose just some random point, look at the derivative. If it's positive, then we make the step to one side. If it's negative, go make a step to another side. Maybe the constant step, maybe non-constant step, it doesn't matter. And do it iteratively. Well, if we make just the constant steps, most likely we will always jump around the real minimum. But if we do it, if this value would depend on the value of derivative, then very quickly we will find the minimum of the function. Well, this is the common approach of gradient descent. We can apply it for well, this is exactly what I was talking about. If we make the step according to the derivative and some coefficient that might be constant, that might be decreasing with every step, or that can be calculated in some specific forms. But this is the general idea that on every step, if we want to find the better solution, better in quotes, because we don't know what is better, but we hope that there exists a better solution, we have to calculate the derivative function. How can we apply it to our case? We want to minimize the sum of errors. Well, in this case, in case of one neuron, there is only one error, and we want to minimize this function. Then by A, we can consider, for example, if A is just the S, or some function on S, it doesn't matter. If S is just the sum of weights and signals, then the derivative of L would be the derivative by W. W is the derivative from L by A multiplied the derivative from A by S and the derivative from S by W. And in this case, taking the derivative from this thing would be exactly this derivative, this function. Yes, 2 on 2, and don't forget to take the derivative by S. If they are the same, there would be not this multiplier. If there is some special function, that we have to make the derivative from F by S from function A. And this is how to say it. This is the very same thing that we did in the common approach of on the previous slides over here, when we added something. Here we say that we have to update the weight W with exactly this value, with the difference between known value and the value that we received over here. We have to add to our weight the difference. Well, in our cases, it was only 1 or 0. So there was not exactly the difference. It was exactly that value, because the difference was whether 1 or 0. But this approach might be applied for several neurons. For example, if we have such net with 2 inputs, let's think that there is no this neuron. For example, there are only 2 of them. on the first layer and on the second layer. And we want to know how can we change this weight. Well, it's easy. The common loss function for this output contains, it is not square, just the index, contains the losses in this step, and in this step. Yeah, so we still should consider this one. So this is the losses from here. This is the losses from here. But both of them also relies on the losses over here. Yes, we don't know which weights are wrong. Only this one or these two are only also wrong. Okay. Okay. The thing that we should how to say it do precisely, we should find out what is the function on the first step. It is well known, just sum of x0 and x1 with this weight, and these two values are calculated based on this value. Yes, since it is divided on 2, on W0 and W1, they are based on this value. So the first thing that we should and now let's think only about the upper neuron. So we want to know how to update these two neurons. For example, we want to update only these two. We know that after some time we will have to update also this one, but let's at least find how to update this pair of neurons. How to update not neurons but weights. How to update the pair that relies on the x0 value. Well, this string is known. It is the same as was over here for one neuron. On the last layer, the rule of updating is straightforward. The complicated part appears when we want to update the weights on the previous layers. And the further we go, the more left we go, the more complicated formula for updating becomes. Because weight 0, 0, this one, depends both on 0, 1 and 1, 1, on these two things. Yeah, it depends on these two because how to say it? Because output is two-dimensional, and we may. So my initial thought that we should not consider this one is wrong again. We should consider everything. For example, if we come with output 1, 1, but the correct output is, I don't know, 2, 100. That means that we have to change every of this weight. It is easy, it is clear for us how to update these two. This formula is known. According to this new weight, we have to update these two weights. And the way how to do it is this one, where we rely on the known deltas. I don't remember the exact name of this updating, back reverse or something like that. It's just a formula that should be, how to say it, proved just once. That should be proven just proven. That we should prove just once and program it just once, and it will work forever. If we would have more layers than 2, we'll just make in the same template we will have one with delta null, delta 0, 2 plus pum with delta 1, 2 on delta and so on, so on. So the general idea that if we have several neurons, we can update the last weights by the gradient descent and back reverse all the weights in the network. And the learning process will be exactly the same as it was before, but here would be a little bit more complicated formula here. But once again, this formula is known. And moreover, never in your life you will program this formula by your hands. It is programmed already for you, and the only thing that you have to do is import TensorFlow. And from TensorFlow, you will be able to use all the functions that you need. Moreover, there are functions .learn and .recognize, something like that. The reason why am I showing it for you is to make sure that you understand everything inside. You will never program it, but you will have to understand how does it work. The classic example of recognition dataset is MNIST. This dataset contains handwritten digits, and this dataset is required to for some networks to recognize which exactly digit is placed on every particular image. The idea is that output here in this possible network that would recognize one of these how to say it, digits, the output contains of 10 values, everything whether 1 or 0, and every this output corresponds to the value 1, 2, 3, 4, 5, and so on. The input here is 28 on 28. I don't remember how much is that. So there are that amount of inputs, 28 on 28. And inside the network, there comes some kind of connections that transfers this amount of input to this amount of output. And the magic that happens inside was described in the previous slides. Back reverse gradient descent. That is done already for you. Unfortunately, I don't have the source code for the network that is already learned, not learned, trained for this data set. But you can find the source code. Maybe I will provide the link by email for the networks that work with the MNIST data set. There are 7 lines. First line, 4, several iterations to learn. Second line, learn. And the third line, try with the other digits. And that's it. The most things with the with neural networks are already programmed in the libraries, and most likely you will never in your life program your own network unless you are the researcher, the scientists. Okay, and the network that I've just described to you is the easiest structure of network. It is called feed-forward network. There are several types of such networks, but every one of them contains somewhere inside the regular network. Let's come through every possible type, and I will show where and in which task one or another network is used. Feed-forward network, exactly the one that I said. As I said, they might be one layer inside or several layers. It doesn't matter. Most area of application for such network is when you always know the output. I mean, for example, if you want to find the exact person on the image, and then if you are looking for exactly known patterns on the image, then you can use feed-forward neural network. For these tasks, exactly this network shows the provides accurate results. Radial network differs only by the activation function. Activation function, let me remind you, is the thing that relies over here. To this moment, we also thought that this activation function is exactly the sum of weights, but sometimes we can add to this sum some probability function to say that if the output is in the neighborhood of some value, then we will multiply it on the great value. If it's far away, we won't multiply it, for example. And this network applies to the clusterization problems. If, for example, we don't know the amount of clusters, or if we don't know how far are the clusters, then we can use these networks. Multi-layer perceptron are the networks when we have all the connections. Here on the previous slides, we didn't say anything about the amount of connections. There might be all of neurons from one layer connected to all of the neurons from the next layer, maybe not. It doesn't matter in the first type of networks. Here we expected every one of the network of the neurons from one layer are connected to every neuron from the another layer. And these networks are most likely used for speech recognition. Somewhere in the Google helper, there is this neural network with this structure. Convolutional neural networks are exactly the networks that are used for our problem of classification and clusterization sub-images on the video frames. The advantage of convolutional neural networks is that instead of whole image that might have the great resolution, we divide it on several images with a lower resolution. We can, well, this image is just the array. We can go through each, not go through, how to say it. We can divide these images on the parts, for example, for 9 pixels. For example, this square is 3 on 3. And we can multiply it on some matrix that makes it from 3 on 3 just one number, or makes it 2 on 2, and convolute in this way this high resolution image to image with low resolution. Not to lose data, to avoid losing data, we can do several such images. But when we do the convolutions enough times, somewhere here, we have still the common fully connected or not fully connected regular network. So the difference of convolutional networks from the regular networks is the initial steps before neural network magic. Another also popular type of neural networks is the recurrent neural network, where the previous neuron outputs something that we use for the new input sample. And it also used in the speech recognition or text-to-speech conversion, it doesn't matter. Well, in working with text, because in text we have a lot of patterns that are not strictly constructed. Is it because that depends on the language? But the patterns exist always. And in this case, we can use the recurrent neural network. And the last thing that not very widespread, but it is worth to mention, it's modular neural networks, where we have several networks inside one huge network. Nobody, how to say it, stops us from having, instead of one perceptron, put here the special network with one input and one output, and to put here anything we want. This type of networks are used for tasks that might be divided on parallel independent subtasks. What is it? Sentence models. I don't remember what is this. What is this? I don't remember. I prepared the slides like a year ago and then don't remember which exactly, what kind of network is this. Okay, let's just pretend that there is no such slide. Basically, that is all that I wanted to tell you today. I, on purpose, didn't show you the examples of networks that do something for us, because I wanted this lecture to be more mathematical. I wanted you to make the first impression of how networks work. On the next lecture, I will show you the example of network that works with the images of the rods, that does segmentation or clusterization. And you will know that after encoder, maybe, yes, maybe. Most likely, yes. Yeah, on the next lecture, yeah, I will show you how to apply, not how to apply, how somebody applied convolutional neural network to segmentation problem in the autopilots. I won't make you program it. I won't make you touch it by any case, because when you start to work with neural networks, you will have to spend a lot of time on training, and you will need a very high performance computer, and you'll have to spend a lot of time on learning, because by learning I mean training of network, because the process of training might take hours. And if we're talking about training on images, where every image is 1 or several megabytes, then you will firstly processing of one image will take some time, and secondly you will have to store this data set of images. And in this case, I don't really want you to train the network by yourself, but I will definitely show you how somebody already trained it and how does it work. And that will end our module that corresponds to the perception. Then let me remind you that in autopilots, perception, localization, planning, and action in the end. So tomorrow, not tomorrow, next week, the last part of the perception and planning, and that will provide you the the complex view of how does the autopilot work. Okay, so far, other questions? All right. If there are no questions, then thank you very much. I hope that after this lecture you have the first impression of neural networks, and if you still didn't work with them at all, and if you will face the problems with the neural networks, you will just know where to start. Okay, thank you for your attention. Bye. See you next week.